All right, so this is the last class before the final exam, and what I want to do is go over the quiz questions first of all. So I've got basically, we're looking at this here, and we're going to go from -8, 0 to 8, 0. Now, it does help a little bit that you know something about the shape, so it's kind of a way you can maybe check your answer at the end. But the idea is, it's more important to set up the integral than it is to integrate the integral. I have to make that very clear. There are an infinite number of variations of this question. I could say y equals anything from one point to another. And the setup of the integral shouldn't take very long, but the integral you come up with, most of the time you won't be able to integrate. I mentioned this for arc length. There's actually only 3 forms of an integral that you can integrate. We did a couple of them in class, and I think we did this one. We did a x to the 2/3 power, and there's one other one. So the interesting thing is there are very few that you can actually do, but you can set up all of them. It just turns out I gave you one that you could actually finish, but the setup again is the most important part. On the final, I might just say set up the integral to give the arc length. So if I write this as 64 minus x squared to the 1/2, then the first thing we want to find is dy dx. And again, in looking at the quizzes that were turned in, most people did a really good job on this. It was very mechanical, but were you just copying down what I had already done? That's really the question. Or did you think your way through the problem? So when I simplify this, I'll put it back over the root. Okay, so I get something that looks like this. Now, the integrand, remember, is 1 plus the square of the derivative. So in that case, that'd be 1 plus x squared over 64 minus x squared. If I put that over one denominator, and that gives me just 64 over 64 minus x squared. Okay, now remember the integral is going to be the square root of this. So let me go ahead and squeeze that in up here. So now the arc length, S equals the integral from, and since we're integrating with respect to x, and by the way, for these, we generally go endpoint to endpoint because again, you're following a curve. This is not area under a region. So it's not automatic that you're going to go x to x. I'm going from this point to this point. It may be the case that you say, you know what? It's easier if I do x as a function of y and then integrate dy. That's totally acceptable. And if you found yourself doing it that way, then of course you would choose the y limits. So in this case here, we're going from -8 to 8. The square root of that, which would be root 64 or 8 over the square root of 64 minus x squared dx. Now that's a little bit intimidating at first. I noticed something here. Okay, boom, boom. Everyone see even function, symmetric limits. Whether I can integrate this or not, I'm going to double it, and I might as well pull the 8 out while I'm at it. So I'm going to write it as 16 times 0 to 8 of 1 over the square root of, how about 8 squared minus x squared? Now, if I write it in that form, hopefully this is automatic. Now, at this point, you've essentially answered the question to the best of your ability if this cannot be integrated. It turns out in this case, it can be. You see, what if I threw a different exponent on here? What if I've got a different coefficient? What if there's just a different root? Then it's very likely that I won't be able to continue, but I've still stated the problem. And again, that's the most important part. In this particular case, we know the antiderivative. This is a straight up formula. I mean, we have a formula. You don't have to derive it, right? A squared minus x squared dx is inverse sine of 1 over a times x plus c. I mean, that's one we know. You don't have to do anything clever. You can write the antiderivative now. The next thing is going to be 16 times the inverse sine of 1/8 x from 0 to 8. So that would be 16 times the inverse sine of 1. Now remember, it's an even function. Because it's an even function, I can do this. And the antiderivative of all even functions are odd functions, and all odd functions evaluated at 0 are 0. It is perfectly correct to put minus inverse sine of 0. In fact, that's good form. It's automatic that that has to be 0 because, again, it was an even function. Now, if I didn't know what to do, I could write this. Now, you're saying, I'm not that good with the inverse trig. So remember, I showed you how to kind of cheat this a little bit. Okay, get out your calculator. Put yourself in degree mode. This is the easy way out. And I'm going to go inverse sine. Okay, inverse sine 1, and it says 90 degrees. I go, oh, okay. So therefore it's pi over 2 radians. So that's pi over 2 radians. So my answer is 8 pi. Yeah, it's good to know inverse sine is pi over 2. But if you don't, you can always use your calculator in degree mode. Now, what if I did that in degree mode and I got some icky decimal? Well, that would just mean my answer is not a common angle. You see, what if the limits of integration were such that this is not inverse sine of 1, but maybe it was inverse sine of, 0.9 or inverse sine of 2/3 or something that's not a common ratio? Then you would actually just leave the answer in that form. Okay, but the final answer is 8 pi. That's beautiful. Again, the most important thing was to get to here. It was the nature of the function that I asked that allowed you to continue, but there's no guarantee. If you go through the problems in your textbook, you shouldn't be able to integrate most of them. The ones you can integrate are the ones that are chosen specifically because they can be integrated, but in general, they may not be able to. So the second problem, I'm looking at y equals 2x cubed. And we're going from 0, 0, 0, 0 to 216. Okay, read my own right here. Okay. Now, it's not important that I can integrate this. It's important that I can set it up. All right, so I'm going to draw a picture here. I've got 2x cubed, which moves very fast. I'm going from here to here. And the reason I want to remind you of this, I gave you a problem that you actually can finish. That's unusual, but this one you will be able to finish. But when you get an answer at the end, how will you know if you did it correctly? Remember, I showed you a simple check. If I find the length of that line segment, the length of that line segment should be shorter than the length of the curve. Not tremendously shorter, but definitely shorter. Now, what's interesting is I did not see anybody do this check when they turned in their quizzes. Most people did it well, but you're saying, I hope I got the right answer. You can actually check it. So again, once I finish the problem, if I compare the length of my curve to the length of this line segment, and let's go ahead and find that first, in fact. Just using distance formula, it's going to be 2 squared plus 16 squared under the root. Well, that would be the square root of what? 256 plus 4, so the square root of 270. Okay, now the square root of 270, if I want to reduce that, root 9, root 30, so 3 root 30. I don't really care about the 3 root 30. I would like to know as a decimal about how big is that? Because this is my check at the end of the problem. That's about 16.43. That's how long the length of the line segment is. And I'm keeping that in the back of my mind so that at the end of the problem, when I get an answer, I can compare the decimals, and my answer better be a little bigger than this one. If it's smaller than this, then I know I've got an error. Okay, so first thing is we find dy dx. Then I find 1 plus the square of dy dx, which would be 1 plus 36x to the 4th. And so my integrand, I'll put over here, my area is, remember, 2 pi times, now we're going to integrate with respect to x, so we're going to go 0 to 2. I have the square root, that's called the arc length parameter. And here I have the function. Some people turned it in and forgot that the function goes, the function goes right here. Okay, that's what we derived in class. If all I had was this square root, then I'm kind of dead in the water. The integral of that root cannot be evaluated. There is no antiderivative formula for that. But at this point, I have correctly stated this is the surface area. If you got this far, then you have done well. It just so happens, though, because of the nature of my integrand there, I have a 4th degree polynomial under the root. I have a 3rd degree polynomial out here. This one is ready to do a U substitution, okay? Because basically the degrees are perfect. So if I let u be the inside of the root, then my du is 144x cubed dx, and that's almost what I have. So the first thing I'm going to do is get that guy out of there, move him in front. Okay, I need a 144 here. And that's how we do it. That's the simplest way. So now let me rewrite this. 4 over 144, that's 1 over 36. So I've got pi over 36. I'll write this as 1 plus 36x to the 4th raised to the 1/2 power times 144x cubed dx. Now I haven't changed anything. I've just manipulated, because right there, there's my 4x cubed, which I started the problem with. But now it's in the form u to the 1/2 du. So the last piece is, of course, to change the limits. And by the way, as a group, we did a very good job. Probably 80% of you did a really good job of getting this far and changing the limits correctly. So as x ranges from 0 to 2, well, let's see, when x is 0, u will be 1. When x is 2, 2 to the 4th is 16. 16 times 36 is 576, plus 1, 577. 577 is not a friendly number. Okay, not at all. There's nothing that I can do with that. That's going to show up at the end of the problem, obviously. So now, when I write this out, I'm going to have pi over 36 integral from 1 to 577 of u to the 1/2 du, and I really like that because that's easy. There's no way you're going to convince me that this one is hard. Now I get an icky numerical value, but the integration is really simple. So I'm going to have u to the 3/2 times 2/3. Times 2/3 would be 2 over 108 or 1 over 54. So I'm at pi over 54, 577. Now 576 is a perfect square. 577 is not, therefore you can't evaluate that. You can give a decimal approximation. Evaluate would be like saying square root of 4 is 2. That's evaluating. Giving a decimal is not an evaluation. That's an approximation. I cannot evaluate that, but I can evaluate that. 1 to the 3/2 is just 1. So probably the best answer, and certainly the one I saw the most of, was something in this form. Okay, leaving 1 to the 3/2 is kind of silly because you can evaluate that. Now, I'm pretty sure I did everything correctly, right? And we're okay with pretty sure. No, I'd like to know. This is my answer. I'm pretty sure I did it right, but now I can compare it to this, the decimal. So when I calculate this, right, when I calculate, whoops. I lost something. Hold on a second. What did I just do? Hang on, I'm gonna try that again. I just lost something in my answer. 577. I think I forgot to divide it. All right, try that again. Okay, well, I got something.
Are you getting 806?
Got something goofy. Yeah, I got, hold on a second. I got 806. Hold on, I think I did a bad calculation over there. 806 point, say 0.28. Okay, hold on a second. So we went from, what didn't go? 0, 0, 2. Hold on.
Is it because we got the area, not the arc length?
No. Oh. Thank you, Gildardo. I was still looking at my answer to problem 1. You're right. Yeah. You know what? Scrap that. Yes, this is the arc length. This was the surface area. Yeah, you are absolutely correct. Oh boy, that's pretty lame. Yeah, I'm not comparing this one. It's the first problem that I meant to compare the first answer, not the second one. Yeah, that is the correct answer. And by the way, most of you did this. Now, this answer here really isn't useful right now because we don't have anything to compare it to. If I'm doing an application problem, whatever this thing looks like, and by the way, some of you drew this, and I think it's wise. we got really good at finding volume. Okay, hold on a second. So I took this thing here and then I rotated it. I'm gonna do my best here, you know. I got kind of that bugle. Okay, I got that bugle. We know how to find the volume of that at this point. Heck, we could do this as a disk. We could do this using shells. I think most of you would say, yeah, the volume of this, trivial, not even challenged. But we found the surface area of this thing, which is way more complicated. But you can't compare the surface areas and the volumes for one simple reason. They're different units. All right, I can't do that. That wouldn't work. So when you're getting an answer like this, you're saying, what do I compare it to? Well, in this case, not really anything. Now, if I'd given you units, what would the units of this be? What sort of things?
Squared.
Unit squared.
Squared units, yeah. And that kind of throws us because we've done volumes and we've done other things, but this is an area. Even though it's three-dimensional, the units of surface area are the same as the units of area in 2 dimensions. And that throws us a lot of times in math because we don't think about that. We think three-dimensional automatically units cubed, but that's actually not the case here. So that's kind of important. Now, going back to the first problem again, we found an arc length. Did you know that the answer was going to be what the answer was? Did anybody know that ahead of time? No. Okay, what is this? This is a circle, terrible circle, but a circle of radius 8 centered at the origin. Okay, what is the arc length of a circle? May I remember? The circumference. What's the formula for circumference of a circle?
Is it pi r
Pi
squared?
times diameter.
Now, pi r squared is the area of the circle.
Pi times diameter.
Pi times, or in terms of radius, we generally say
2
2
r
pi
pi.
r. Yeah, and the reason you usually use radius because the radius shows up in the calculations for spheres, for everything. So it's usually, yes, it's pi times diameter or 2 pi r. All right, so what's the circumference of the circle? It's 2 pi times 8. Okay, what was our curve? Our curve was this. What is this in comparison to that circle?
A semicircle.
But which semicircles, very specifically?
The one in the northern hemisphere.
Yeah, the Canadian part, I guess, right? How do you know it's the top half? Because it's y equal positive square root, which means y is non-negative. So basically the question on problem 1 was find the arc length of a semicircle. Oh, you mean I could have just done this? Well, this is a way you could check your answer. So our answer should have been half of this because we did half of a circle, and that was our answer. Now, it's good that you could do the calculus. By the way, be honest, how many, blurt out if it was you, how many actually checked their answer by just comparing it to a circle? Did anybody do it? Now that you're going, oh my God, I could have just checked it versus, yeah, but the point being you found it using calculus. Oh, and by the way, how do you suppose that formula was arrived at in the first place?
It has to be aliens.
Yeah, it's calculus. Yeah, the formula for the area of a circle, for the circumference of a circle, for the surface area of a sphere, for the volume of a sphere, those absolutely required calculus. They didn't come from anywhere else. And now that you understand the calculus part, oh my God, there's so many things I can now do, because now you can take shapes that aren't perfect circles. Maybe you have an ellipse or something that's not exactly the same, and you can actually then figure out area. There is a simple formula for the area of an ellipse, but you don't actually learn that formula till the end of calculus 3, because you can't actually calculate it using calculus 1 or calculus 2. But the area of an ellipse is cool because it's not complicated. The formula is not complicated. The derivation of the formula is pretty gnarly. Okay, we have covered everything. We've looked at everything. So now the exam, Thursday morning, obviously, I'm assuming everybody is taking it unless they've contacted me. And only a couple people have actually contacted me about saying, I'm not going to take the final. So if you aren't, I really would appreciate an email. Otherwise, the morning of, I'm worried like, okay, why haven't they checked in yet? Now the final itself, like we said before, everything's fair game, but it's only going to be the big ticket items. right? You're going to do derivatives, you're going to do limits, you're going to do integrations, you're going to do applications, you're going to do graphing concepts. And that's basically it in a nutshell. You're not going to do the fringe things. You're not going to do the stepping stone things. You're not going to do any definition of the derivative in order to get the derivative. No, that's limits. You got the derivative formulas. You're not going to do epsilon delta in order to get the limit. You're not going to do the summation formulas in order to get the integration. Okay, I'm not asking for that. You're doing the finished works. You're going to do every problem that I ask, because I'm not asking that many of each thing, except in one part, I've given you multiple application problems and you get to choose. I think there's one part where I give you 5 applications and you're going to choose 3 of them, because all of the applications are important and relevant, but from a time standpoint, it would be difficult. Can you do extra ones? Well, obviously, yes. But like always, don't do extra ones your first time through, because then you might run out of time later on. There's no extra credit on the final, because extra credit would only be relevant if it was recent material. If I asked an extra credit question from 3 months ago, no one would remember how to do it. The other thing is I have to leave off a significant amount of stuff. So to put an extra credit in lieu of something else, no, extra credit is over and above challenge, but you guys have had enough extra credit problems on the exams and enough bonus questions along the way that when I was going through the quiz scores, I was amazed at how many people have 100 or more points of just bonus over and above how much the quizzes are actually worth. The quizzes are worth 750. I've got many people with well over 800, 850 points on quizzes. That's really, really good work, folks. That definitely makes it a little bit easier on you at the end. Now, yours is the 3rd of 4 finals, but I fully expect I'll be done with them no later than Saturday. And I point that out because I know some people are needing their grade in order to register for summer school. I'm going to give you an example. I know some of you are planning on taking my accelerated 6-week course that starts in 13 days. Yikes. Yeah, there's not a lot of summer going on before the class, but then there's a lot of summer at the other end. But the reason that's important is you want to know if you succeeded in this course. But then again, nobody should be signing up for that course unless you're doing really well in this course anyway. So I will have the grades posted during the weekend at the absolute latest. And part of the reason I do that, it's actually not for you, believe it or not, it's for me. See, I don't get to start relaxing and taking a breath until I click submit and all the grades are in. So I'm in a hurry to get that done. Technically, the grades are not due for several weeks. And I'm not going to wait to turn in the grades because then it leaves me hanging. In December, that's the worst. Grades are not generally due until the end of the first week of January. But you had your finals 3 weeks earlier, maybe more. But a lot of instructors say, no, I'm going on vacation and I'll come back and get to my finals. Not me. No, I get my finals done, then I can go on vacation. I'm just the opposite. So that's where we are. Everything that you've learned in this course, like I said, is fair game. But again, the big ticket items. If you look at the practice final that I gave, the final looks just like that, but it's exactly what you expected. But you don't see detail-oriented questions on that practice final. You see big stuff. And big applications, right? Optimization, maybe a related rate, things like that. Can you find a volume? Can you find the surface area? And the integrations. So you get to bring a formula sheet, as I mentioned before, 8.5 by 11, one side. I would strongly urge you to go back through your formula cards that you use and say, what do I need for the final? Because there's probably a lot of information that you don't need to put down on because you now know it really, really, really well. I really don't think you need much of any derivative formulas. You should concentrate on the antiderivative formulas because that already contains the derivative in reverse. But there's a lot of things, trapezoid rule and Simpson's rule are formulas. Newton's method is a formula, right? Tangent line estimations is a formula. These are things that most of you did very well on, but some of it is not recent material. And that's really important. On the problems that we just did today, there were some incorrect formulas for surface area and or arc length. So got to make sure you write those formulas correctly. Arc length is 1 plus the square of the derivative under the square root. Surface area has exactly the same thing, but also multiplied by the original f of x. And that sometimes gets left out. So do due diligence on creating your formulas. If you haven't already done so, that might be even more important than some of the review, because I'm not expecting you're going to remember every formula. I'm expecting you're going to know how to use every formula. And when I ask you an integration question on the first problem on today's quiz, I would hope that everyone looks at that and says, oh yeah, that's inverse sine. But some would look at it and say, I don't see it. But that's actually straight up a formula, no derivation required. Okay, some folks are still deriving their formulas when they integrate, even though we already have a built-in formula. I don't need you to derive formulas, but I do need you to do correct substitution. So at this point, I'm going to stop recording.